I was looking at your quiz.
I know I've written this 1B. I just completely forgot the zero.
Right. I think your idea was right. The trading and all the other ones are correct. This one, I think it's okay because y is the summation and they are all integers, they're all discrete. So the summation, which is the maximum of x1 and y is discrete. So it is a reasonable idea to calculate those two. But then the final number was not right. Because you get for y equal to 1, that must be they all equal to 1. So you should multiply like x1 equal to 1, x2 equal to 1, x3 equal to 1. If one of them equal to 1, that must be x equal to 1, so that's 0.3. So for this one is 0.3 to the power 3, right?
Yeah.
And then for this second one, 4 equal to 2, you have to, this is the maximum equal to 2. So there must be one of them equal to 2, all the other ones equal to 1. That's the only possible. No, actually more than that. It could also be all of them equal to 2, the maximum equal to 2, right? So for the y equal to 2, it's actually more complicated than just one single calculation. Yeah. So you have to calculate 2, 1, 1, 1, 2, 1, 1, 1, 2, which is similar to 1. And then you also have to calculate 2, 2, 1, 1, 2, 2, and then
2, 1, 2.
Right. So and then the last thing you have to calculate 2, 2, 2 because so you're gonna that is 7 situation, and you have to add up all
the
7.
probability.
Yes. So that you didn't show the calculation, so I don't know how that will be calculated.
Okay. That makes sense. Thank you.
You're welcome. All right. Surprisingly today, okay. Hi Giselle. I see Giselle. So let's try a question for attendance. This question, it was calculation of a probability about the mean. Because it's talking about the mean of 25 random variable, so this is actually a central limit theorem question. So let's try this one as a attendance question. All right, normally the kind of calculation depend on the question itself. This question, this says we want to calculate the probability that the average of 25 randomly selected claim exceed 20,000. So we're really calculating probability that the average is higher than, we're calculating probability that the average number is higher than 20,000. Right. So because of the question that we want to calculate, we gotta know what exactly X bar is distributed. Now, that is the reason we will go for the central limit theorem. The information itself says the claim, which is X follow a normal distribution. The mean is 19,400. The deviation is 5,000. So that means the variance is 5,000 squared. Deviation is 5,000 there. And so when we would apply central limit theorem, and we know that the distribution for X bar, and that's the reason that we would use normal distribution to answer this question. According to central limit theorem, what should be the mean?
1940.
It would be the same, right? It would be 19,000. And the variance is different, right? The variance should be the original variance divided by n, and in this case, n is 25. We're going to take 5,000 squared divided by 25. And if you want to find the standard deviation, you have to take square root. So this calculation is equal to probability that Z is higher than, you're going to take the 2000 and minus the mean, minus say 19400. You will divide by the standard deviation, so that's the 5,000 is the square root of the integer. Square root denominator will be 5. So that actually is basically 1,000. So the denominator is really 1,000, and we will calculate the Z value from the right side of the inequality. Once you get the Z value, you have to use a probability table to find the probability. You can find a probability table, or you can run the article or if you want. Right. Finish the calculation for the R. We are calculating probability for bigger than, so it's like 1 minus the p of the Z that you calculated, but we don't know the Z yet. So you finish calculating that Z. This is the Z that goes in. This Z.
About 1.6.
Are you already finished?
Yes.
You got
0.6.
0.6 for Z.
Okay.
So this is a probability that Z is bigger than 0.6. Okay. And so that is 0.6 here. And then we can run our code, or you can use a normal standard normal deviation chart. That's what I have. A regular normal distribution table will give you the same answer, standard normal distribution. Add one. Right, so we need the 0.6. Okay, that will be the 0.6. All right, that will be the 0.6, and you have to do 1 minus, right? It's the right side. It's the probability to be bigger than. So with 1 minus that table value, we should be able to identify the probability to be exceeding the 20,000 mark. Anyway, so that's the overall calculations. So if you're ready to submit, let me turn on the app. Close the app up to show. We have the answer, okay. Let's see. So the answer is a 0.27, as we had over here. So 0.27, or you can use 1 minus 0.275. So the same answer with the table or with the computer. Do you have any homework question?
5.5, question 12.
5.5, number 12.
I think so.
Okay. Go to the OneDrive. Five, number 12. This question?
Yes.
So we have one normal distribution and one chi-square distribution. And we did a division. That will be that y1 is a normal distribution divided by square root of the chi-square distribution over R. That is a t distribution, right? So we were to find the joint probability density function. I remember the t distribution in the book. It was given by the CDF approach. Here it wanted us to do the transformation approach. So it's kind of like confirming the same answer, determining the marginal distribution of Y1, which should be the same as in the section. This is all verification of what's already shown. Show that Y has a t distribution. So what was your main difficulty?
Just finding the joint PDF. Because I forgot, because I forgot that Y1 would equal a t distribution. I hadn't realized that yet.
Yeah, well, here it said that x1 and x2 are independent. So in order to find their joint distribution, we would use the transformation approach. So you would find the inverse transformation, and then you can use the original density, like x1, x2 are independent. So you can multiply the density function for x1, x2. Because of independent, you're allowed to multiply their density, and that is a joint density for x1, x2. To find the joint density for y1, y2, you find the inverse transformation and plug in there. So we follow what's in section 2. I might have the solution in my folder. But I think this one we can use what's already been given. We had the standard normal distribution density. We can multiply. Let me try to write it out here. Let me copy this question. Right, so first we will find the joint density between x1, x2. So then that will be like f of x1, x2 is equal to, right? This, we're able to write it because x1, x2 are independent. So you would write the density for x1, which is normal, so it's 1 over root of 2 pi. You can go to section 6.3 to confirm, but the density function is for standard normal distribution is 1 over root of 2 pi. A normal distribution is I think it was negative, it has a square in the, this is x1 squared over 2. That's the density function for x1, and then the density function for x2. It was a chi-square distribution. That was 1 over gamma. This is a 2 to the power r or 2r. Let me try to confirm that. I think we write out the density function. By the end of section 5.4, I was trying to summarize all of the density function and moment generating function for some of the common distribution. In 5.4, yeah. It's gamma distribution. So this is supposed to be 2r. Theta equal to 2, and this is this should be 2r minus 1, is it? Right? For the relation between gamma distribution and chi-square distribution, the theta equal to 2. So theta equal to 2, alpha equal to r over 2. Yeah, so this is R over 2. Okay, just try to compare. Gamma, this is a gamma distribution density, but chi-square distribution is a special gamma distribution. So this is supposed to be theta over alpha. Theta is 2, alpha is 1, alpha is R over 2. And this is supposed to be x over alpha minus 1, so this is x over R over 2 minus 1. And then you have e to the negative x over theta, and theta equals 2. So this is a gamma distribution density, and x is a gamma distribution, x is a chi-square distribution, which is a special gamma distribution, and then we have a normal distribution. You multiply them, give you the joint distribution for x1, x2. And what we're going to do, we find the inverse transformation. You already have the transformation from x1, x2 to y1, y2. Say x1 over root of x2 over r. And this is the y2 equal to x2. That means the y2 basically is like something that goes with it. So the main target is really y1. So if you want to write inverse transformation at x2, so we're supposed to write x1 and x2. You want to have a representation so we can plug in, right? So x2 equal to y2, so that way you can directly write it. x1 is supposed to equal to y2 times the denominator, but y1 times the denominator, but x2 equal to y2, so it's really y1 multiplied by root of y2 over r. So that's the inverse transformation. So once we have the x1, x2, we can plug in to find, this density function. In the meantime, we also need to know the Jacobian of the inverse transformation. So we would find the derivative of x1 with respect to y1, which is root of y2 over r. And then derivative of this function with respect to y2, that was y1 over r over root of r, that was coefficient. And we will find root of y2 because of the root derivative function is you move the power to the front and the power minus 1. So it becomes 1 over 2 times root of y2. This was an r. And the denominator is the derivative of x2 with respect to y1, that was 0, with respect to y2, that was 1. So when you cross multiply, the Jacobian is root of y2 over r. And that was the one we were multiplying. So to finish with A, you will write f of y1, y2 would equal to 1 over root of 2 pi e to the negative x1, and that was x1. So you would square the y1, you have y1 squared, and this is multiplication, so multiply by y2 and divided by r, and there's a 2, so there's 2r. So that's the e part. And there's no change to the denominator since they're just coefficients. It's supposed to be gamma r over 2, 2 to the r over 2, x to the power r over 2. This is x2. That was x2. x2 is x with 3. So change this one. X2 is actually y2. So y2 to the power r over 2 minus 1. And then e to the negative y2 over 2. So this finished the substitution part. And then we're going to multiply the Jacobian. So that will be the y2 over r. Any question? And then you're probably going to combine like terms. The exponential part, like this one will combine with this one, and then you will combine the power part, the y2 to the power 1/2. There's a y2 to the power r minus 1. So the 1/2 power plus the -1 power give you -1/2. So kind of change that part. This is a root of r. We already have a r to a certain power. That would be in here. I guess that should be combined in here. R to the 1/2 power. So I think we might combine some like terms in terms of power and terms. Hopefully it will get you ready for B. Part B, you have to integrate what you have in the part 1. If you want to get rid of the y1, you have to dy1, right? You have to integrate the density function, integrate the joint density function to find the marginal density for y2. If you are integrating over y1 and you see only this part, the part that actually related to y1, so all the other one, in terms of your integration, the y2 will be kind of like a coefficient. You move it out, and these are going to be part of the T distribution coefficient. T distribution function. I think that should be most of the main thing for the proof. This is kind of like a proof because we already have the T distribution density. Your answer to part B should be the T distribution density as in the section. I think you might be able to see it in the book. It was in the same section. The T distribution density was this one. So once you finish it, you see we would have a root of pi. We would have r to the 1/2 power already. We have r to gamma r over 2 already in there. So many of the terms you see once you finish calculating it, they will be part of the answer. I hope that's okay.
Yes, thank you.
Let's see. Any other homework question? Giselle, do you have any homework question?
No, ma'am. Thank you.
For the quiz last week, I didn't see anyone that has like completely correct for everyone. So yeah, Michael had same error as yours. But he was calculating the y less than 2 term by term. 1, 2, 3, 4, 5, 6, 7, 8. Then the answer should be like, yeah, I think Michael might have every answer. But I didn't really update the quiz 1 grade because I feel like we all have 1 or 2 problems. So let me explain the solution to that question, and then if you want to, you can take it again. But I'm probably going to change the number again to make it a new version of it. Right, let me see if I can explain the solution for quiz 1. So this is a question that we had last week. Let me right. Basically, we're trying to go over if you have multiple variables, how to handle the calculation for the probability or the density function. This belongs to 5.3. The first question, we're looking at a geometric distribution. So that's when you try something over and over until you have first success. So according to the probability, the success rate is 0.3, the failure rate is 0.7, 70% failure rate and 30% success rate. If you want to determine the probability x1, x2, x3 add up to 4, since every geometric probability you have to start with 1, and you have to try it 1 time to have at least 1 success, right? If you're the x represent total number of trial, how many times you have to try something, so x star was 1. So the minimum value for all x1, x2, x3 is 1. And to make a total of 4, there are a couple of scenarios. You can have x1 equal to 1, x2 equal to 1, and x3 equal to 2. Or you can have x1 equal to 2, x2 equal to 1, and x3 equal to 1. Or you can have x 1 to 1, right? So this is all possible scenario to have a total of 4. There are only 3 scenarios. So what you can do is calculate one of them because x1, x2, x3, they're random sample of the same distribution. They're independent. So if you want to calculate the first one, it would be the same as calculating the second one. So this is really 3 of the same calculation. So you calculate probability of 1 time probability of 1 and time probability of 2 from the geometric distribution. So if you want to calculate probability of 1, it would be that was a probability. It would be 0.3. Because if x equal to 1, 1 minus 1 is 0, 0.72, 0 equal to 1, right? So this is going to be 0.3. And then last question for probability equal to 2, the x equal to 2. 0.3 times 0.7, so then it's actually 0.21. The result of 0.3 times 0.7. And then the rest is just working with numbers. So I'll read that for the calculator. So part A. Part 2, the y is representing the maximum. So if you want to have a probability y, the maximum of x, the maximum between x1, x2, x3 is less than 2. So then everyone have to be less than 2, less or equal to 2. So all you have to do is making sure that x1 is less than 2, less or equal, and x2. This is an and relation, that's why I multiply. X1 is less than 2, and x2 is less than 2, and x3 is less than 2. I do multiplication because they are independent. So that's what we are really supposed to calculate. Let's see how to calculate probability x1 less than 2. For a single variable to be less than 2, that means less or equal, that means probability 1 plus probability 2. So it's 1 or 2, right? X less or equal to 2 means x is equal to 1 or x is equal to 2. There's the 2, right? So we will calculate probability that x equal to 1, plug in x equal to 1, that's 0.3, plus probability x equal to 2, that we already calculated is 0.3 times 0.7 is 0.21. So if you combine them, you end up having 0.51. That's probably x1 is less than 2, but it will be the same, right? For x2 less than or equal to 2 is also 0.51. So the actual calculation means that this is going to be, apply this, it's going to be 0.51 times 0.51 times 0.5. So we actually are going to multiply all 3 to get 5 minutes. Hope that can make sense. That's the solution for both questions in question number 1. The second question, and we have distribution for x and distribution for y, and we want to find out what is the probability x minus y is bigger than 0. So the question will be, if you want to study the probability of x minus y, what kind of distribution is x minus y? So we know that x follows a normal distribution. There's 10 and 16 as variable, as variance. Y is following a normal distribution. The mean is 11, the variance is 9. So what about x minus y? X minus y, the mean is
-1.
-1. Then the variance is It is,
16 plus 9, right?
yes. 16 plus 9, which is 25. That's the variance. So now we know the distribution, and we also know it's a normal distribution because the xy is normal, so x minus y must also be normal. And that's something that normal distribution added together is normal. Normal distribution subtracted is also normal, so that's something we can get from section 3. So what we see that if you want to calculate the probability about x minus y, you can calculate the z value for the question. So we convert the 0, 0 has to minus the mean. The mean is -1, so we minus -1 divided by the standard deviation. Variance equals 25, and the standard deviation is root of 25, which is 5. So 0 minus 1 is 1, so 1 over 5 is 0.2. So this probability z is bigger than 0.2. Right, so you're going to go 1 minus the probability to be less than 2. That's phi 0.2. Or the p-norm 0.2 if you're using the R coding. And then we can use a distribution table or the R coding to find the answer. So that's the final answer. I'll leave the rest of the calculation for you to check out the normal distribution. And that's the solution to the quiz. I hope that kind of gave us some idea. We're going to try again. We can have another set and try it. But I think you probably can get like 80% because you only made a small error. Giselle, do you have any questions?
No, I don't. Thank you.
So today let's try to finish what we left of section 5. That is we did 5156, which is normal distribution related question, and 5.6 is central limit theorem. Central limit theorem. We started talking about last time we started with 5.7. That is sometime for a high number of sample size, the calculation of some of the discrete distribution can be hard. For example, in the binomial distribution, the trial number is 200. Then the probability calculation can be very time consuming. Use just normal distribution, binomial distribution, so we can use normal distribution to approximate it. Similar to Poisson distribution, if you have a mean that equal to 552, then calculation for probability that x is between 10 and 20 will be calculation of 11 number. You're using Poisson distribution formula. But with normal distribution, we're able to approximate a lot faster. For example, this question, you get a Poisson distribution with mean 20. You want to calculate probability y, which is a Poisson distribution between 16 and 21. What you can do that, you want to create a correction of continuity. In a continuous distribution, you want to be able to include the probability of 50, actually probability of 70, 17, 18, 19, 20, and 21. So in order to include all that, we're creating the boundary of 16.5 and 21.5. That way those integer is in the range, and we convert the number by minus the mean divided by the standard deviation, converting it to a normal distribution question. And then with a normal distribution table, we can find the probability, which is close to the Poisson formula answer, but not exactly, they're not exactly equal, but it's pretty close approximation. Any question? So if you want to connect the Poisson distribution with a normal distribution, you have to do this. The W equal to y minus lambda divided by root lambda, which is here. Minus 20 divided by root 20, that convert all the end and the boundary into a z value. All right, that's the homework for 5+7. I think we finished most of the questions for 5+7 last time. And the only section left of the chapter 5 is the Chebyshev inequality. With Chebyshev inequality, we're able to create, define a new kind of convergence. It's called convergence in probability. Convergence is a very popular idea, concept in calculus, right? We talk about convergence of a sequence, convergence of a limit, convergence of the integral. Whenever you have a limit value that approaches a certain number, you have a convergence now. So this also is another limit. Whenever we talk about convergence, there must be some limit that we involve. Well, let's start with the Chebyshev inequality. All right. What is a Chebyshev inequality mean? It actually is an inequality showing that this probability is bigger or equal to something, and we focus on the central probability of any distribution. The reason almost every statistic or probability book have to talk about Chebyshev inequality because this inequality applies to all distribution. It doesn't matter if it's uniform, normal, exponential. They all follow the same rule. If you have a minimum percentage of central percentage, so it doesn't really give you the exact probability. They give you the probability has to be bigger than certain number in the center. The main idea of central Chebyshev theorem is telling us the majority of any distribution is in the middle, which is around the mean. So for example, where we're trying to say many times you use sample mean to approximate the population mean, but how good that estimation, and it depends on a certain number we call in normal distribution we call z, right? If you wanna find the switch standard deviation around the mean, of course your percentage in the middle is high. If you only have 1 standard deviation or 1.5 standard deviation around the mean, the percentage should be lower. And we give a minimum value for that percentage. Here we use an example for one of the examples that we can apply Chebyshev theorem is when binomial distribution. So suppose you try manually trial n time, that would be a binomial distribution. If you use the number of success, which is y, divided by the total number trial, which is n, and that's a division. That division is a probability, or you can call that a proportion. So y over n is a proportion. We often use y over n to approximate the population proportion. So how good is that estimation? So that's something that we want to use Chebyshev's inequality to show. All right, so let's start with the inequality. Okay, what is the Chebyshev inequality? You can write it both ways. You can use Chebyshev inequality to represent the tail probability or represent the central probabilities. But whichever way, bless you.
Thank you.
Whichever way you want to write your inequality, you want to make sure it is correct. Let's start with talking about the tail probability rather than the center. And let's try to write it. We'll compare the two different ways to what Chebyshev inequality. All right, so this is the one that starts by talking about the tail probability. What do we mean by tail probability? Let's say you got a distribution, and this is the center, which is a mean. Okay, so you want to move a certain amount of standard deviations. This is k times standard deviation. Let's start with k equal to 2. So I have to be able to draw something. So k equal to 2, we will move 2 standard deviation above. So we have plus 1 standard deviation, 2 standard deviation. This is the upper bound. Right, and start from the mean, you go 1 standard deviation below, 2 standard deviation below, you get lower bound. So between mu plus 2 standard deviation and mu minus 2 standard deviation, between these two boundaries and the central percentage, what do you think? The central percentage is quite high in the sense that it has to be bigger than 1 minus k squared. All right, so we're saying doesn't matter what's the distribution, it could be bell-shaped or exponential, but the middle is the most. That's why we say in the middle percentage, we don't know exactly what is the percentage. We know that percentage is, let me just call that P. The middle percentage is bigger than 1, bigger or equal to 1 minus 1 over k squared. That leave all the percentage on the outside. This tail is the right tail. This tail is the left tail. We see the left tail and the right tail together. It's small. How small? It is smaller than 1 over k squared, right? For the same reason, because the middle already is higher than 1 minus k squared, and the force outside will be smaller than 1 over k squared. So this saying that the probability of, when you write it both ways, probability that x minus mu, x and mu distance is higher than k standard deviation, which is x and mu is further apart. This probability is smaller than 1 over k squared. Or you can also say it backwards, saying that the probability that any given data, which is x minus mu, is it less than k standard deviation? Right? What does this mean? It means x minus mu is really close, which is smaller than k standard deviation, and then bigger than negative k standard deviation, right? If you have an absolute value sign, if you remove the absolute value sign, you're adding a positive upper boundary and negative lower boundary, right? That is the absolute value. When you see absolute value of something less than a positive number, mean this subtraction is less than this, bigger than this. If you add mu to both sides of the equation, we mean this data is less than mu plus k standard deviation and is smaller than mu minus k standard deviation, right? So this is saying this data is within like certain amount standard deviation to the mean, which is really indicating x is right in the middle. All right. Up there, they are bigger than means that x is bigger than mu plus k standard deviation, or x is smaller than the mu minus k standard deviation. So the upper one, the red one, it means that x, which is a beta value, has to be either in the upper tail or lower tail of the probability curve, if we have any curve. In this question, I can't draw any curve because it doesn't have any requirement for the underlying distribution. So that is saying that this percentage is going to be big. It's bigger than 1 minus k 1 over k squared. You see that this two, the red one and the green one, they actually mean the same thing, right? They're opposite. X minus mu bigger than the k standard deviation, which is x and mu, are further apart because the x minus mu is so big that x must be away from the mu, right? So the top one saying, if you look at the tail, the one that's far away from the mean, then you have a very small amount of data, right? If you look at the middle, which is close to the mean, that number of data, that percentage, p as in percentage probability or proportion p, that percentage is higher than 1 minus 1 over k squared. So think about the main idea of the Chebyshev theorem is basically saying the tail has smaller probability. This probability has to be smaller than 1 over k squared. The middle has to be is bigger than 1 minus k squared. So because there are two different ways, we kind of have to have the ability to identify which case are we talking about. Are we talking about the middle? Are we talking about the outside percentage? I hope I'm making sense. Because you can see different versions of it. Sometimes our textbook is representing Chebyshev in this way, like you see a 1 over k squared. And sometimes you see a 1 minus k squared, the formula of Chebyshev. You'll be wondering, why are we having two different ways of it? They actually mean the same thing, even though they're saying like, because the negative and negative is positive, right? They actually mean the same thing. Another way to make sure we're guaranteed we're not writing it wrong is looking at the middle. So this is bigger than, this is less than, right? It's like certain amount of symmetry. You got this on this side, you must have this side on the other side, on the outside of the key. If you have this is less than, you must say this one. So if you have this one, you must say this one. Like they're always like symmetry, like symmetric, right? So you never have bigger than and bigger than, or less than and less than. You'll always have, if this is bigger than, this is less than. If this is less than, that's bigger than. So if you want to keep track of the inequality sign that involved in the Chebyshev theorem, you realize you won't be able to write it wrong. But the one minus k squared or the k squared, 1/k, I cannot guarantee that part. This part, you have to remember the reasoning, right? The middle gotta be more and the tail gotta be less. I hope that makes sense. So that's the Chebyshev theorem statement. Let's talk about a proof. All right, so we want to prove this. And then this proof also is very classical in a way that we don't have any information for the underlying distribution. How do we get the information? How do we make that inequality? So we're going to start with the definition for the variance. The reason that we start with definition for the variance because we have x minus mu there. We know that exploitation of x minus mu squared would be the variance. So start with the variance, you automatically have x minus mu in the formula itself. So variance equal to exploitation of x minus mu, and this x minus mu in the discrete case, it will be a summation, right? It's summation of x minus mu times the probability. So this is how you calculate the variance. So the first row last term is a formula for how do we use a summation to calculate the variance. And then this summation involves many data points. So x is in the S in the support. So the data point can be the part that's in the middle or at the tail. So we're going to separate A representing x minus mu bigger than k times standard deviation. A represents the tail number, tail data. So the variance, this summation have to involve the data point, the number that's in A, and the number that's not in A. So we're able to separate the variance calculation into two parts. And then because the variance calculation includes the summation, if we remove one, we remove the x belongs to A prime. That is the set notation saying x is in A prime. If we remove that one, that means this becomes smaller. So if you only have this one, it will be less of the variance, right? The variance involves the summation. So if you only have one of them, you're reducing the quantity, right? So we have a bigger or equal than symbols. We have this. All right. So we do have the standard deviation in the original definition. We have k times standard deviation. So then we're bringing that into the formula because that's definition of A. All right. So now we have this. The variance is bigger than this. Now we already knew that because of the definition of A, x minus mu is bigger than k times standard deviation. So this x minus mu is bigger than k times standard deviation. So we switch the x minus mu in that third row for the k times standard deviation in the fourth row. All right, after we've done that, we have this inequality. Interestingly, we have standard deviation, we have variance in both left and right side. We divide out the variance, right? And then we divide out the variance, then we will have 1 is bigger than k squared times this, right? And then we divide the k squared from both sides of the equation, that will be the last inequality. So the proof is very smart. So it's a tricky way to combine definition of variance and the set notation in the process of the proof. So that's not required, but you might mention that in your proof theory class. Right. So another way to represent the Chebyshev theorem is remove the k times standard deviation with the word epsilon. Switch out that with epsilon. The process is kind of like this. And then this is like another version of the Chebyshev theorem. Write it out. I mean, sometimes this equation is more useful. All right, according to Chebyshev's theorem, it goes like this. Probability that x minus mu is bigger than k times standard deviation. K is common standard. K is kind of like the z. All right, according to Chebyshev's theorem, you see that it is bigger than, so we go less than or equal to 1 over k squared. And that was a Chebyshev theorem. So if you switch out one of these things, you switch this for epsilon. All right, so if they're equivalent, then obviously epsilon is equal to k times standard deviation. So that means that we have this, then we have k is equal to the epsilon divided by the divided by the standard deviation, right? So because of that one we have x minus mu is bigger than epsilon after the substitution is less than 1 over k, right? K equal to this, so 1 over k is reciprocal. So we're going to reciprocal this one, which is this squared over epsilon squared, right? Let's basically switch out. So the relation between the two equality is a simple substitution. You substitute epsilon for k times standard deviation. As a consequence, you will substitute the k by epsilon over standard deviation. That's how we end up. So this gives us a way to arbitrarily write that thing. Right? We have to write it. But there's this requirement, according to Chebyshev theorem, k gotta be higher than 1. It has to be bigger than 1. Therefore, as a result, this epsilon has to be bigger than the standard deviation. So if you choose an epsilon that's really small, that can be a little bit conflicting. K is too small, then the right side of the equation end up being too small, and then it ends up being not that useful anymore. So we should choose larger epsilon to sense the equation. And so that's this corollary. All right. What's the implication? I mean, I already talked about. Basically, it says that the probability x differ from its mean by at least k standard deviation is less than or equal to 1 over k squared. Which really is the tail is actually pretty smaller than 1 over k squared. Therefore, the middle percentage will be larger or equal to 1 minus 1 over k squared, right? Like this. So the third line, the third sentence is actually somehow somewhat will represent Chebyshev theorem, and therefore you have this consequence. This is your equivalence. So switch k times and division. That's something like this. Okay, so that we end up having maybe a 4 different version of the Chebyshev theorem. But this 1 over k, 1 minus 1 over k squared or 1 over k squared, they're not exact probability. They're the boundary of the probability. So we cannot treat it for the actual calculation. And it says here, in many situations, this boundary is not very close to the true population, to the true probability. So we have to watch out that they give you a bound that's not accurate, but it's give you a certain boundary, so you will not go in the wrong direction. All right. Some of the textbook want us to find percentage of a boundary for the probability using the Chebyshev theorem. So this is one of the questions. Suppose we have a variable that has mean 25, a deviation of 16, a variance of 16. Then the standard deviation equal to 4, so we can find the boundary for lower bound for probability x is between 17 and 33. Realize 33 minus 25 is 8. 17 minus 25 is negative 8. So this has a deviation of 8. This has a deviation of negative 8. So we realize that the data that within this boundary minus 25 will have an absolute value less than 8. That reminds us the Chebyshev theorem. And also because 8 is twice the standard deviation. Standard deviation is 4. So 8 equal to 2 times standard deviation. Apply Chebyshev theorem. This inequality goes with this inequality. So less than it goes with the bigger than sign. So this probability is in the middle of the distribution. So this is why it's bigger than 1 minus 4. 1 minus 1 over k squared. The k equal to 2 in this case is 8 equal to twice of the 4. So the k is number of standard deviation. Then we have 1 minus 1 over 4, which is 0.5. Any question? All right, we can switch this probability to a bigger than 12. 12 is 3 standard deviation. In that case, k equal to 3, and therefore it will be less than 1 over 9. The 9 is 3 squared. So that's applying the Chebyshev theorem for the other direction. To look at the tail rather than the middle. Any questions? There is a few more questions applying similar than like the 5.8 number one. So we could apply more questions similar to this one. Do you have any questions? So first example is when k equal to 2, we're looking for middle, probably middle. The second one, the bottom line, is when k equals 3, we are trying to find you apply Chebyshev theorem to the tail. The probability of x minus mu is bigger than 3 times the equation. All right, let's apply Chebyshev's theorem to the binomial distribution. Like I said, you can use the number of success divided by n. Y over n is actually a proportion. So according to central limit theorem, y over n has a roughly normal distribution. When the sample size is large, y over n has a normal distribution with mean equal to p and variance equal to n times p over n. So with Chebyshev theorem, we're able to write this formula. Right, when p is unknown, when the percentage is unknown, we often use y over n to calculate or to approximate the underlying percentage. All right, what's related to the Chebyshev theorem is this part. I guess we should mention the Chebyshev theorem one more time. Probability that x minus the mean is bigger than epsilon. This probability is less than 1 minus, it was a standard deviation squared over epsilon squared. The bigger the epsilon, the bigger the distance, the smaller the probability. Maybe I got it wrong. It's 1 over k squared or squared over epsilon squared, right? It should be a smaller probability at the tail. So applying that to the binomial distribution, in a binomial distribution, we see that if y is a binomial distribution, then y would follow. If you look at normal, y is a summation of a probability distribution, so it would follow mean equal to nt and variance equal to n q. Right. So as a consequence, if the y is a sum, right? It's a summation. So y over n is the mean of the binomial distribution for success. So this is the following a normal distribution. When the n is large enough, it will follow a normal distribution. The mean is np divided by n, which is really p. And the variance will be individual variance, which is pq divided by n. Okay, this is the difference between the summation, applying central limit theorem summation. This is applying central limit theorem to mean. That's what we have. So as a result, if you are applying this probability for binomial distribution, now we have y over n is our variable, and the mean is p instead of mu. So replace the mu by p bigger than epsilon, which is less than. So here we're gonna keep the epsilon squared in the denominator. We're gonna replace the variance by pq over n. Over n. That's a connection here, just because that one was supposed to be the variance for y over n, y over n's variance. I'm just trying to explain that first rule of calculation. What does it mean? If you switch out the inequality sign, and then you're going to have to switch out the equality sign, the second equality sign, also have to switch the boundary to 1 minus the quantity. So, any questions so far? So starting with the equivalence, the second rule of calculation, we can calculate this limit. This limit for when n goes to infinity, then this n goes to infinity. PQ over n, when n goes to infinity, that has a limit 0. So this probability would have a limit 1, because this is bigger than this. The smaller one have limit equal to 1, and probability is naturally less than 1. So this probability is bigger than, the limit of this probability is bigger than 1. And then it also smaller than 1 by definition. This is a probability. And therefore, it would equal 1. So that as a consequence, using the squid theorem in calculus, it's bigger than 1 and also it's smaller than 1, so therefore it must equal 1. So we know the limit of the this probability is equal to 1. So the probability that y over n minus p less than whatever boundary you give it equal to 1. That probability equal to 1. Because if you make n goes to infinity, the y over n in the probability term, it equal to the underlying probability when the sample size gets bigger and bigger. Any question? I think this was also called the law of large number. As you increase more and more of the sample size, the probability or the percentage you end up calculating equal to the true underlying probability. I hope that can make sense. So whatever difference you're choosing to make it, that one is for sure is less than that number, because y over n and p is almost the same. And the sample size is large enough. So this is called a convergence in probability. Converges in probability to p. So y over n converges to p, but not in the calculus term, not in the quantity term, it's in the probability term. So then this, we also have this, together we have another law. It's called a law of large numbers. That is, the sample size converges in probability to the population mean. And that was verified in the binomial case. Already verified here, now we can also verify the same thing. If you make n goes to infinity, the x bar approaches to mu in probability. That convergence is guaranteed because of Chebyshev theorem. So we can actually connect the Chebyshev theorem with the law of large numbers. Any question? I mean, law of large number is a theoretical foundation that bigger sample size is always preferred over smaller sample size. Because if you collect more data, naturally you are getting more accurate for the underlying situation. Like, it always better to collect 20 data rather than 10 data. The only thing that stops us from collecting more data is we may not have enough time, we may not have enough people, we may not have enough equipment to collect more data. But larger sample size is always preferred. These are the homework that I assigned for 5.8. Any question? All right, try and see if it's have any difficulty. Again, try to let me know. This Wednesday, we're gonna quiz over 5.5 and 5.6. So we're assuming that we already finished with 5.3 and 5.4. But if you have any questions, you're welcome to try to get them. But we finally finished chapter 5. The main idea of this second half, the 40 probably a statistics working we'll get the question. It's working on statistics, so we'll at least start a little on chapter 6. All right, let's go over a little bit of 6.1. All right, we're gonna talk about statistics. I assume you guys already have some elementary statistics, so some of these might feel like a review when we at the end. So, but we're doing a little bit more coding, so hopefully many of the examples that we had can confirm what we have already learned in the past. So 6.1, the title is called Descriptive Statistics. So we're gonna look at what is statistics exactly and what is descriptive statistics, what's differential statistics. So basically, statistics can be divided into two main categories. The first one is descriptive statistics. It's kind of like in the name, it's describe what was exactly in your data. And the second stage or second part of statistics is inferential statistics. That is, you go to the bigger picture. The reason that we collect data, we describe what's going on in the data set that we already have is in order to find out what is the underlying truth, right? So sometimes we interview people, you might interview like 20 or 30 people in order to find out their opinion. And your ultimate goal is not exactly what their opinion. You actually try to find a broad audience, like everybody's opinion, right? The ultimate goal is what's going on, what is everybody thinking about this? So inferential statistics, you apply what you already have to prove of the overall picture of the overall population. So we have to say inferential statistics has bigger impact, but it all depends on if you have a correct calculation or have the right data for your descriptive statistics. So descriptive statistics is a foundation, and inferential statistics is the conclusion or the final impact. All right, so let's look at the descriptive statistics. You can think of two of the main things in descriptive statistics is number one, you want to be able to organize the data and display them. You can display the data with visual pictures. You can also display data with tables and formulas. All right, and the second part is not only do you have to display them or organize your data that you collected, you also have to figure out some of the main measure. Right, as far as this, right, if you want to display the data or visually draw the data out, you have to think about what kind of data do you have. For qualitative data, we normally use bar graph or pie charts. And for quantitative data, you can use dot plot, stem plot, or histogram. So these are some of the common ways to display data. So you have to look at what kind of data you have in order to determine the right way to display them. Right, measure. There are more than two measure actually, but I'm putting two of the main measure. Almost all data you at least have to do two different measure, and they always go hand in hand. So for example, if you use the mean to measure the center of the data, you will almost always use the standard deviation to measure the deviation or variability of the data. Now, if you use a median, do you know what's a median?
What was that, sorry? What was that, sorry?
Median? What's the median of the data?
No.
Median. If you order the data from small to maximum, like, in order.
Median. Oh, yes.
Yeah, the median. Yeah. Median of the data set, suppose you use a median as a measure of the center. Talking about measurement. And almost always you would use quantile and range, interquartile range to identify the variability. So the way we measure center variability, there are a couple of ways to do different ways to measure center, different ways to measure variability. All right, so that's just a review. And then for inferential statistics, we can roughly divide them into two types of inferential statistics. We can do estimate, we can do hypothesis test. So estimate, we have point estimate, we also have interval estimate. Point estimate is try to estimate, like say you want to estimate how much a TV costs. You can estimate like roughly $800 or 800 to 1,000. So estimating use a single number is a point estimate, saying that the TV for this TV is roughly to $800. So that will be a point estimate. But when you say the TV is between 800 to 1,000, you're giving an interval. Okay, so obviously giving interval is more likely to be correct, right? There's always deviation when you say something is 800 or 700 and you go to the store, it's not that value. So you always buy off a little, but if you're giving an interval, very likely it's the right amount of money. Right, that's estimation when you want to find the value of something. The other inferential statistics is hypothesis tests, right? So for example, we have test for the mean, test for proportion, test for differences, and then test for multiple means and test for multiple proportions. So there are a lot of different hypothesis tests. The main goal for most hypothesis tests is to compare plan A, plan B, which one's better, right? This decision and this decision, which one is correct? So most of the time when you do a hypothesis test, your ultimate goal is to compare. So are you trying to estimate or are you trying to compare? But you can always do both. I mean, sometimes if you compare with something, that gives you some idea what the value, right? It gives you some hypothesis test might give you idea for the estimation, or the estimation might give you some idea for your test. Right? So they can go hand in hand. That's why we always present them together. All right. So let's first talk about what is statistics exactly. I sometimes just making sure and calling statistics is a science of data. But there's a lot of things about data that we would have to do in the science of data. So what do you do with data? You collect them first. They don't automatically be there. You have to find out where the data is. So data collection is one of the things. It's actually a big subject in statistics. If the data was biased, if the data was wrong, if the data was corrupted, and then of course everything you do will fail. So number one, we have to have the right data. And then what's called in data collection, I believe we will always talk about how do we collect data. You can collect every data in the population. That will be a census. Very much in many situations it's very time consuming. And so most of the time we do sampling. We collect a subset of the population, and we have different sampling methods. There are like a stratified sampling, cluster sampling, right? Different sampling methods. There's simple random sampling, systematic sampling. Right. Once we have data, the second stage of the statistical work is to display and organize the data. And we didn't mention the organization depending on the data type. All right. Once you organize data and display the data, we want to have a data summary or measure the data. So once you have those measure and summary, you're able to do some more calculation. So the next stage is the actual data analysis. You can do confidence interval calculation, hypothesis test, and you can do both. And then with those hypothesis tests or confidence interval, you're able to make decision or draw conclusion. Right? The conclusion, you might have to use some common sense to think about it. Once you finish all the numbering, all the calculation, you want to see if it actually makes sense. If it doesn't feel right, if it doesn't make sense, you may have to redo the whole process. If not, we'll stop at the conclusion. If it seems right, and then somehow we'll go with that decision. So this is the cycle of data analysis, cycle of statistical work. All right, time. All right, just try to introduce this a little. I mean, many of the things you can read about in the text, but we're gonna talk about it when we come back. That will be it for today. I guess we'll only have this little much time. All right, so try to finish up all your homework for 5.5 and 5.6 this Wednesday. If you got any question, we'll talk about the question first. If there's no question, we'll start the quiz on Wednesday for one of the assignments. And that should be it for today. Giselle, do you have any questions?
No questions. Thank you so much.
Thank you. That'll be it. Thank you.
Okay, bye.
See you Wednesday.
See you Wednesday.
Bye, Giselle.